Well, hello. Welcome to video number 1 on waves, which is in your physics paper 2. There are more videos to follow, but this is covering some of the basics. First of all, let's just remind ourselves what waves do. Put simply, waves do one job. They transfer energy. They move energy from one place to another, but they don't transfer matter or stuff. Please don't call it stuff in your exam. I've done a terrible drawing here. Imagine you're on a little boat, just sat there doing some fishing out in the deep blue sea, and as the waves roll underneath you, all they do is they move your boat up and down. They don't take your boat with them. So the waves right by the shore might push you in once they're breaking, but those aren't the sort of waves we're talking about. So remember, waves transfer energy. The energy rolls into the shore, but the boat just bobs up and down. So waves do not transfer matter. Okay, you need to know about two types of wave, and you need to know them in a bit of detail. So here we go. The first one is transverse waves. They're the ones that are this S shape. And when I say transverse, I often say transverse to remind myself that that's the S shape. Okay, when we look at the wave, you can see that this diagram shows that it vibrates up and down. The physics word we use is oscillates. It oscillates up and down. You can also see from this arrow that it's transferring energy, in this case from the left to the right of the picture. Good examples of this type of wave are the surface waves in water, for example in the ocean, light waves, radio waves, X-rays, and in fact all electromagnetic waves, which includes light, radio and X-rays, are all transverse S-shaped waves. You need to be able to describe them properly, and you need to use these words. Transverse waves oscillate, you can say vibrate. Perpendicular, you could say right angles or at 90 degrees too, but perpendicular is better, to the direction of energy transfer. So you can see from our diagram the energy is transferring that way, but the oscillation is at 90 degrees to that. So we describe transverse waves of oscillating perpendicular to the direction of energy transfer. It's really important you say that. If you get asked to describe a light wave, you need to write those things. Okay, the other kind, and you might remember your teacher showing you a slinky spring with these types of waves, is longitudinal. And you can remember because it goes along the wave, so it's longitudinal. In this case, the oscillation or vibration is back and forwards. And the energy again on this diagram is being transferred to the right. And the only really good example of this for you is sound waves. That's the example to use. And you need to be able to describe this kind of wave as well. And here, the longitudinal waves oscillate or vibrate parallel to the direction of energy transfer. Okay, you could use the words wave motion, but energy transfer is better. So longitudinal waves oscillate parallel to the direction of energy transfer. Okay, last bit for this video is about some properties of waves. Things we can measure, and these always come up one way or another. So here is a transverse wave I've drawn on there for you, and you need to know firstly that the very top point of the wave is called the peak, and the very bottom point is called the trough, and this line in the middle is called the equilibrium position. Okay, you could also call it, if you wanted to, the rest position. If you can't remember equilibrium, you can call it the rest position, but it's the middle bit, the middle line. We've got two measurements that we can make that are both distances. The first one is called the amplitude, and it's the height of the wave from the rest position to the peak, or from the rest position to the trough. It isn't the double height though, so the amplitude is just the size of the wave or the height of the wave from the rest position either to the peak or trough. It's not the double height. The other measurement we can take is the length of the wave, called the wavelength. And you might remember the symbol is this upside down Y shape called lambda. And to do it, the simplest way to get the wavelength is to measure from peak to peak. If you can't do that, then the other simple one is to go from the rest position past the first rest position to the next rest position. So don't forget, one wavelength is that shape there. That is one wavelength. With regard to longitudinal waves, similar but different. In this case, we've got the areas where the wave is squashed together, and that has a special name, which is called compression, which you need to know. Compression means squashed. And if you measure the distance between the centre of two compression points, that will give you the wavelength of that wave. By the way, you also need to know the bit where the wave is spread out is called rarefaction. Rarefaction, and that's that part of the wave, so you need to know those. You need to know the definitions of wavelength and amplitude, so here they are. Wavelength, again the upside down y or lambda, means the distance between two identical points on adjacent, that means neighbouring waves. And if you look back to our diagram, that was what we did. So we picked two identical points, the two peaks, on neighbouring waves, and we measured the distance between them. The amplitude means the distance from the equilibrium or rest position to the peak or trough of the wave. And again, we did that on our diagram a minute ago. Okay, so that's the start for waves. That's Waves video 1. Please check Waves video 2 for more.